We start our excursion with Earth, not to learn anything, just to get a dubious feeling of scale. The littlest things that have some star-like properties are huge gas Goliaths or sub-earthy colored smaller people. Like Jupiter, the most monstrous planet in the planetary group. Multiple times bigger and multiple times more gigantic than Earth, and that's only the tip of the iceberg or less, made of a similar stuff as our Sun. Simply a whole lot less of it. The progress towards stars starts with earthy colored midgets, bomb stars that are a colossal disillusionment to their mums. They have somewhere in the range of 13 and multiple times the mass of Jupiter. So regardless of whether we took 90 Jupiters and tossed them at one another, albeit enjoyable to watch, making a star wouldn't be sufficient. Strangely, adding loads of mass to an earthy colored predominate doesn't make it a lot greater, simply its internal parts denser. This expands the tension in the center to the point of getting specific atomic combination responses going gradually, and the items sparkle a bit. So earthy colored midgets are a kind of glowy gas Goliath that fit into no class well overall. In any case, we need to discuss stars, not bombed wannabe stars, so we should continue on. Primary arrangement stars. When huge gas balls pass a specific mass edge, their centers become hot and thick enough to light. Hydrogen is melded to helium in their centers, delivering huge measures of energy. Stars that do that are called fundamental grouping stars. The more gigantic a primary succession star is, the more sweltering and more brilliant it consumes, and the more limited its life is. When the hydrogen-consuming stage is finished, stars develop, up to a huge number of times their unique size. Yet, these monster stages just keep going for a small part of their life expectancy. So we'll look at stars at definitely various stages in their lives. This doesn't make them less noteworthy, however perhaps it's great to remember that we'll contrast children with grown-ups. Presently back to the start. The littlest genuine stars are red smaller people, multiple times the mass of Jupiter, scarcely monstrous enough to combine hydrogen to helium. Since they are not extremely enormous, they are little, not exceptionally hot, and sparkle pretty faintly. They are the main stars in the fundamental grouping that don't develop once they kick the bucket, yet kind of flame out. Red midgets are by a wide margin the most plentiful sort known to man. Since they consume their fuel gradually, it endures them up to 10 trillion years, multiple times the ongoing age of the universe. For instance, one of the nearest stars to Earth is a red small star, Barnard star, yet it sparkles too faintly to be seen without a telescope. The following stage are stars like our Sun. To say the Sun rules the planetary group isn't doing it equity, since it makes up 99.86% of all its mass. It consumes far more sultry and more splendid than red diminutive people, which decreases its lifetime to around 10 billion years. The Sun is multiple times more monstrous than Barnard star, yet that makes it almost multiple times more brilliant, with 2 times its surface temperature. We should go greater. Little changes in efficiently manufacture huge changes in a primary grouping star's splendor. The most brilliant star in the night sky, Sirius, is 2 sun-powered masses, with a sweep 1.7 times that of the Sun. However, its surface is almost 10,000 degrees Celsius, making it sparkle multiple times more splendid. Consuming that hot decreases its complete life expectancy by multiple times, to 2.5 billion years. Stars near multiple times the mass of our Sun have surface temperatures almost 25,000 degrees Celsius. Beta Centauri contains 2 of these gigantic stars, each sparkling with multiple times the force of the Sun. That is a great deal of force coming from something just multiple times bigger, yet they'll just consume for around 20 million years. Whole ages of these blue stars kick the bucket in the time it takes the Sun to circle the cosmic system once. Anyway, is this the equation? The more gigantic, the bigger the star. The most gigantic star that we know is our 136A1. It has 315 Sun-oriented masses and is almost 9 million times more brilliant than the Sun. But, regardless of its gigantic mass and power, it's scarcely multiple times the size of the Sun. The star is so outrageous and scarcely kept intact by gravity that it loses 321,000 billion tons of material through its heavenly breeze each and every second. Stars of this sort are incredibly interesting on the grounds that they disrupt the guidelines of star development a smidgen. At the point when supermassive stars are conceived, they consume incredibly hot and splendid, and this blows away any additional gas that could make them more huge. So as far as possible for such a star is multiple times the Sun. Stars like our 13681 are presumably shaped through the consolidation of a few high-mass stars in thick star framing districts, and consume their center hydrogen in 2 or 3 million years. So this implies they are interesting and brief. From here, the secret to going greater isn't adding more mass. To cause the greatest stars, we'd need to kill them. Red Goliaths. At the point when primary arrangement stars start to deplete the hydrogen in their center, it contracts, making it more blazing and denser. This prompts more smoking and quicker combination, which stands up against gravity and makes the external layers grow in a Goliath stage. What's more, these stars become really monster without a doubt. For instance, Gocrux. Just 30% more gigantic than the Sun, it has enlarged to multiple times its range. In any case, when the Sun enters the last phase of its life, it will enlarge and turn out to be significantly greater, multiple times its ongoing span. In this last period of its life, it will swallow the inward planets. Furthermore, assuming you feel that is great, we should at long last present the biggest stars known to man, hypergiants. Hypergiants are the monster period of the most gigantic stars known to man. They have a tremendous surface region that can emanate a crazy measure of light. Being so enormous, they're fundamentally blowing themselves separated, as gravity at the surface is too feeble to even consider clutching the hot mass which is lifted away in strong heavenly breezes. Gun star is 25 sun-powered masses, yet multiple times the sweep of the Sun, a blue hypergiant suitably named for its lively blue starlight. It's difficult to say precisely the way in which long Gun star will live, however most likely only a couple million years. Significantly bigger than the blue hypergiants are the yellow hypergiants. The most very much examined is Rho Cassiopeia, a star so brilliant it tends to be seen with the unaided eye, despite the fact that its large number of light a long time from Earth. At 40 sun-oriented masses, this star is multiple times the range of the Sun and multiple times more brilliant. In the event that the Earth were as near Rho Cassiopeia, all things considered, to the Sun, it would be inside it and you would be exceptionally dead. Yellow hypergiants are exceptionally intriguing, however, just 15 are known. Lived middle of the road state, as a star develops or contracts between different periods of hypergiantness. With red hypergiants, we arrive at the biggest stars known to us, likely the biggest stars even conceivable. So who's the champ of this crazy challenge? Well, truly, we don't have any idea. Red hypergiants are very brilliant and distant, and that implies that even minuscule vulnerabilities in our estimations can provide us with a gigantic safety buffer for their size. More terrible still, red hypergiants are planetary group estimated behemoths that are blowing themselves separated, which makes them harder to quantify. As we do more science and our instruments improve, anything that the biggest stars will change. The star that is as of now remembered to be among the biggest we've found is Stephenson 218. It was presumably brought into the world as a fundamental grouping star, as several times the mass of the Sun, and has likely lost about a portion of its mass at this point. While ordinary red hypergiants are multiple times the size of the Sun, the biggest good guess places Stephenson 218 at 2,150 sun-oriented radii and sparkling with close to a portion of multiple times the force of the Sun. By correlation, the Sun appears to be a grain of residue. Our minds don't actually have an approach to getting a handle on this sort of scale. Indeed, even at light speed, it would take you 8.7 hours to go around it once. The quickest plane on Earth would require about 500 years. Dropped on the Sun, it would fill Saturn's circle. As it develops, it will most likely shed much more mass and psychologists down into one more sweltering hypergiant stage, gather weighty components in its center, before at last detonating in a center breakdown cosmic explosion, giving its gas back to the system. This gas will then proceed to shape one more age of stars of all sizes, beginning the pattern of birth and passing again to illuminate our universe. Thanks for watching. Subscribe for even more fascinating videos like this.